think you can open the hatch?
I was just saying to Mike earlier, I've been in the UK for 26 years, and this is the first time I've given a presentation in South Africa since I left, and I'm also going to a conference next week. So it's been a long time coming, but I'm really pleased to be able to do this. So what I'm going to tell you about this evening is the Cassini spacecraft mission to Saturn, which ends in 3 weeks. It's been there since July 2004. It was only supposed to be there for 4 years, but things were going so well and the instruments and the spacecraft was doing so well that it continued to be extended and extended. And in fact, in 3 weeks' time, it's going to burn up in the atmosphere of Saturn. And right at the end, I'm going to show you a movie which shows what we think is going to happen. And I'm always glad that the lights are down, because I must confess I get a bit of a lump in my throat when I see it. But I'd like to start off with this view here, because this was actually an image of Saturn which was taken by Cassini. And it's not a single image, it consists of lots of different photographs that were all put together to show the view. And you can see the sun coming just from behind Saturn here. You can see the planet itself and all of its glory. You can see all the different rings. And those of you with good eyesight who are sitting close to the front can see it looks like a plume of something coming off from somewhere. And in fact, this is a plume of water vapor, which is coming off from one of the plumes called Enceladus, and I'm going to describe to you how my team actually discovered this. And the reason that you can see it on numerous occasions is that these were lots of images that were put together over a period of time. So you can see how the moon was orbiting around us. So just to give you an idea about how big the mission and the team is, these are all the different countries that are involved in the Cassini spacecraft mission. It actually consisted of 2 different things. One is the main spacecraft, which is still orbiting, and that was built by the space agency in the States, NASA. And the other bit was this little gold-shaped semicircular object, which was called the Hercules. And that was built by the European Space Agency, and that actually detached from the spacecraft back in 2005 and traveled down through the atmosphere of Titan, one of the largest moons of Saturn. The reason we were interested in Titan is that we think its atmosphere is very similar to what the Earth's atmosphere was like when it first formed, and so we wanted to try and understand that. The other reason I show this is it shows you the large boom sticking off from the side of the spacecraft. Now, I'm responsible for the magnetometer instrument on the spacecraft, and what that does is it measures the magnetic field in the vicinity of the spacecraft. But if you think about it, you don't want to be measuring the magnetic field due to the spacecraft. You want to be measuring that due to the environment. And so the ideal thing you do is you get as far away from the spacecraft as you can. And so what we do is we put ourselves on this very long boom. It's 11 meters in length. One instrument is halfway down the boom, and the other one is right at the end. And so that means we measure the magnetic field of space rather than that of the spacecraft itself. This shows you a view of the Cassini spacecraft before it was launched, because what you need to do is you need to make sure that the spacecraft and the instruments can operate in the environment of space, which is a vacuum. You also need to make sure they can survive the temperature ranges. I'll show you how we got out to Saturn, but we actually flew past Venus first, and that's really hot. It's about 110 degrees Celsius. Out at Saturn, the temperature is about minus 170 degrees Celsius, so you need the instruments to be able to survive that range. This gold foil that you can see here, covering most of the spacecraft, that's a thermal blanket that helps to keep the instruments at a temperature that they can actually operate. And you can see people standing here, so it gives you an idea about how large the spacecraft is. It's about 2 stories tall. And the other thing you might notice is that the boom, which has my instrument on it, isn't there. But it is actually there. It's folded away into this canister, because you can't launch a spacecraft with a large boom sticking off on the side. So what happened after launch is the boom was deployed, and that's when we started taking it. This big white thing is the high-gain antenna, and once a day for 8 hours, the spacecraft turns the high-gain antenna at the Earth, and it sends the data back down to the Earth. These are the 2 instruments, or the 2 parts of the instrument that I'm responsible for. This one here, known as a flux gate magnetometer, that was built at Imperial College, and that's halfway down the boom. This other magnetometer, known as a vector helium, that was right at the end of the boom, and that was built by part of my team based at the Jet Propulsion Lab in California. And unfortunately, this instrument stopped working about a year after we got to Saturn, and that made life rather difficult for us, or rather complicated rather, in that one of the things we need to do is we need to know what the zero level of the instrument is, because if you see changes in the magnetic field, you want to know where the zero level is, and you can know whether those changes are important. And without two working instruments, you need to roll the spacecraft to be able to calibrate. And we've had to make some changes in how we do our science because the instrument on the end of the boom stopped working. So this is a rather busy figure, I'm really sorry. I just want to give you an idea about how we actually get out to the outer solar system. This is looking down on the north pole of the ecliptic plane. Here the sun is. This is the orbit of Venus. That's the orbit of the Earth. That's the orbit of Jupiter there. And then this is the orbit of Saturn. And so what happened is we were launched on the 15th of October, 1997, so we're not quite going to make 20 years. We're going to be just shy of 20 years before the spacecraft mission ends. We had two flybys past Venus, one past the Earth, there's gone there, and then one past Jupiter. And the reason that we do that is you can't launch a spacecraft as large as Cassini with enough fuel to get straight out to Saturn. And so what we do is we fly past other planets and we gain energy from them. It's almost like two billiard balls, one stationary and one moving. And if the moving one bumps into the stationary one, it gives it a bit of energy and it gets it moving. And that's what we do, is we use planetary flybys to get a bit more energy to get on out to where we want to go. Now you need a lot of patience to be involved in outer planetary missions, because from when you first start thinking about them, it sometimes takes 25 years before you start getting the data back. After launch, it took us 6.5 years to get out to Saturn. So we reached Saturn on the 1st of July, 2014. Okay, so I'm not going to be able to talk about all the science that we do with the data that we get, because there are 11 instruments on board Cassini, and we all have different science topics that we want to focus on. But there were 4 main areas that we thought we would focus on once we got there. One of them is Saturn itself and the rings. The other one is Titan, which is the moon I mentioned to you, and you can see in this view here of Titan the very deep atmosphere. The atmosphere is about 900 kilometers in height. We also wanted to get a better understanding of a lot of the moons of Saturn. Saturn is the only planet in the solar system which has got more moons than we can count. Every time we go to Saturn, we find more moons, and at the moment I think the count is 63. And that's not counting the moons that are in the rings. One of the things we found with Cassini is that within the rings themselves you've got these tiny moons that are orbiting around, and they're actually changing the shape of the rings as they're orbiting around. And then the 4th area we're focusing on is the region around Saturn, which is protected from the effects of the solar wind coming off from the sun. I'm not going to talk about all of that, I promise. There are 2 things I'm going to focus on. One is the moon Enceladus, where my team discovered the atmosphere, and the other one is Saturn itself. The end of the mission orbits were planned with my instrument in mind and the gravity instrument in mind, because what we want to do is try and understand the interior structure of Saturn. So those are the 2 topics I'm going to talk on. And before I move on to the end of mission work, which is Saturn focused, I'm just going to show a few slides describing the Jupiter spacecraft mission, which Mike mentioned earlier. And I'm going to be 68 when we get there. So, young, yes. Well, you were about to say that, so of course you'd say that. Okay, so I'm going to keep this as light on gory details as far as the instrument data is concerned as I can, because only people that build instruments can get excited about wiggles on a plot. But one of the things that you will need to get a better understanding about how we made the discovery is to understand what a magnetic field is. Now, if we stand on the surface of the Earth and we've got a compass in our hand, the needle of the compass is going to point to the north pole of the magnetic field. And so, if you could see the magnetic field, this is what it would actually look like. You have these red lines, which are essentially lines of force. If, for example, those of you who did physics at school, science at school. If you've got a bar magnet underneath a piece of paper, and you've got iron filings on top of that piece of paper, those iron filings will lie along the lines of force of the magnet. And that's essentially what the field lines are. And so if you could see them, this is what they'd actually look like. And at the Earth, they go from the South Pole to the North Pole. Those are the arrows. At Saturn, they go the other way. The other thing about the magnetic field that is generated in the interior is we've always thought that the only way in which it can be generated is by a process known as planetary dynamos. And we've always thought that if say, that's the rotation axis of the planet, so that's the axis about which the planet rotates for the Earth once a day, then that axis needs to have a tilt with the magnetic axis. So there needs to be a tilt between the two. Without them, we don't think the magnetic field can be generated. But at Saturn, we can't find that tilt. And that just doesn't make sense at all. So that's what we're going to focus on at the end of the mission. The other thing you need to think about is that a planet rotates on its axis once a day. So if that's a field line, in one day, one field line is going to rotate all the way around. And if you're a moon in the way, then that field line is going to hit on the surface of the moon. And that's an idea I want you to keep in mind when I show you some of the data. So, this is Enceladus. This is a view which was taken by the camera called Cassini, two separate views which are put together to try and give you an understanding about what the surface looks like. And the first thing you'll notice is there are hardly any craters on the surface. If you compare it to Mimas, which is a moon close by, Mimas is covered in craters. And so people have always wondered, is there something going on at Enceladus that is resurfacing it? Is there something coming up from underneath that is covering up the craters? So that was one thing. The other thing is that there are these cracks that you can see on the surface. And it's actually in the inner region, close to Saturn, where there's a large ring. I'll come back to this. This shows you a schematic of the Saturn system. So here's Saturn. Here are the visible rings. In fact, the first view that I had of Saturn was as a child in our garden in Durban. My dad built a telescope, and my sister and I were so proud of ourselves. We mixed the concrete for the base of the telescope. And then the first view that we had of Saturn was through my dad's telescope. And we could see this little ball with these rings around it. And I never thought 45 years ago that I'd be working on a spacecraft mission at Saturn. But, so this is Mimas, that moon that I mentioned that's covered in craters. So that's how far away it is from Saturn. This is Enceladus, the interesting one. And there's this large ring known as the E-ring that you can't really see. It's very diffuse, but there's lots of water vapor in it. And so people always wondered, maybe Enceladus is somehow the source of the E-ring, but they didn't understand how that could be. So let's just go back to this one here. So, in 2005, so about 6 months after we entered into orbit at Saturn, there were 3 flybys by Cassini of Enceladus planned. The first one was a distant flyby. So Enceladus is quite small, its diameter is 500 kilometers. The first flyby was just under 1,300 kilometers above the surface. A month later, there was a second one planned, which was 500 kilometers. And then 3 months later, there was a third one planned, which was originally planned to be 1,000 kilometers away. But based on the observations we made, we were able to persuade the Cassini project to take us much closer on the third flyby. So, I've talked about that one. Now, this is magnetometer data. If you think about it, a magnetic field is a vector, so what you need to do is you need to measure the 3 components of the vector. You can then work out the direction of the magnetic field and its magnitude as well. And so this is essentially what we've got here. We've got 1 day's worth of data, 24 hours worth of data. We've got, it says X, Y, and Z, but it's not. We've got the radial component of the field, which points away from the planet. We've got the dipole, or the north-south field, which gives you an understanding of the field pointing southwards. And then you've got the azimuthal component. And what you can see on this one is there's almost a wave on the data. And that's another story. We won't get into that tonight. And this is the magnitude of the field here. Now, if you let your eye follow this wave here, you can see that something else seems to be going on here. And just before this signature, it gets very noisy. And just afterwards it gets very noisy as well. You have a look at this component, and again there seems to be, this is the general trend of the data, but there seems to be something going on there. Those of you with really good eyesight will see there's a little pimple in the data there, and one in the magnitude there. And that was the flyby of Enceladus. So there seemed to be something going on. We didn't understand what it was. So what we did is we subtracted the magnetic field of Saturn away from the data to see if we could get a better understanding. And then what we did is we plotted it in a view where we're standing way above Enceladus. So this is the North Pole of Enceladus. We're looking down on the North Pole of Enceladus. Saturn is off here somewhere. The magnetic field and the plasma coming from Saturn are coming from the left here. And this is the spacecraft motion. Flew along in this direction here. And these little field vectors, these little arrows that you see, are the magnetic field which we think was coming from Enceladus. It's got nothing to do with Saturn because we've subtracted the field of Saturn away. And what it seemed to be telling us is that instead of being able to penetrate down onto the surface, it was almost as if they were being held upstream. There was something holding them upstream of the moon. Almost like Enceladus was a much bigger obstacle than it looks. In addition to that, there was this large increase in wave activity. I pointed out to you there's a lot of noise in the data that you can see there, and you can actually work out what ions are generating the waves, because you can work out what the gyro frequency of those waves are. So what the data was telling us, we thought, was that somehow Enceladus was stopping the magnetic field of Saturn penetrating down onto the surface, but also there was a lot of water group ions as we got close to Enceladus. So we put this little, well, not movie, but little thing together to describe what we thought we were seeing. So assume you're standing way above the North Pole of Saturn. So we're looking down on Saturn's North Pole here. Those blue lines are the field lines of Saturn as they're rotating once a day. These are the rings. And the little orange ball is Enceladus as it's orbiting around Saturn. If Enceladus was a dead body, the blue lines, the field lines of Saturn, would move straight through it, wouldn't see it at all. But instead, what we seem to be seeing, and now we're looking at a slightly different view, we're looking sideways on. So we're looking at Enceladus here. These are the magnetic field lines of Saturn coming towards Enceladus. But it saw Enceladus, the field lines saw Enceladus, and they weren't able to penetrate down onto the surface. So they were being draped upstream of Enceladus. And one way in which you can do that is if you have an atmosphere. And the upper regions of the atmosphere become ionized by solar radiation, and that stops the field lines being able to penetrate through. So what we did is we put a schematic together. Because if you think about it, showing people wiggly data on a clock doesn't get them enthused and excited about it. So we put the schematic together which showed what we thought we were seeing. So what we thought was here's Enceladus, and we thought we were seeing a large, extended, diffuse atmosphere covering the surface of Enceladus. And this was after the first two flybys. And so what I did, there was a meeting at the Jet Propulsion Lab just after we had this data. So I went out to the lab, and I said to them, we thought we were seeing an atmosphere, we weren't sure, because one of the things that I was concerned about is because we were flying past a moon, the spacecraft was moving really quickly, so we could be taking pictures as we moved past. And it takes a little bit of time for us to get the spacecraft motion back in high resolution. And so maybe we hadn't calibrated the data properly. But the fact we'd seen it on two flybys meant that we were almost certain there was something there. So we described what we thought we were seeing. And one of the concerns is, you know, when you're planning a spacecraft mission, you've got all these instruments wanting to take data at the same time. They all want to point in different directions at the same time. So in fact, we had spent the first 6.5 years after launch, the 6.5 years it took us to get to Saturn, we spent planning all the observations that we were going to make, down to the last second. And we were always worried, what happened if we'd made a discovery of some kind? Could we change the observations that we were going to make? And the Jet Propulsion Lab said yes, we could. So this was the first test of it. So it took a little bit of persuasion. Not everyone thought it was the right thing to do. But they agreed that on the flyby in July, I think it was 3 months later, they would lower the flyby altitude from 1,000 kilometers down to 173 kilometers. And I didn't sleep for 3 or 4 nights before the flyby, because if we'd seen nothing, no one would ever believe anything I said again. But, luckily, what we saw was something very different. It wasn't an atmosphere covering the entire surface, but it was almost like a cometary plume of water vapor coming out from the South Pole. And this was the water vapor that we were seeing in our data. But because we went so close, all the other instruments were able to take really good data as well. And I'm going to show you data from some of those instruments. So, this is data from 2 different instruments. The first one, to the left, is just from the visual camera. And you can see one of the new things we spotted is that there are these cracks at the South Pole, which the imaging team called tiger stripes. This is data from another instrument, which is an infrared instrument, and what it's able to do is to remotely measure the temperature of the body that it's looking at. That's what they thought they would see. They thought that the hottest temperatures would be in the equatorial regions, because that's where the solar radiation is strongest. But in fact, I mean, they did see hotter temperatures at the equator, but they found that there was this huge hotspot right at the South Pole. Now, when I say hot, it's all relative terms. We're talking about 85 degrees Kelvin, which is about minus 110 degrees Celsius, because it's quite hot out there. So if you overlay this temperature map on top of this visual map here, the hottest spot was right over the crack. And so what we were seeing is there was internal heat coming out from the interior of Enceladus, bringing water vapor with it, and essentially this huge plume of water vapor coming out from the South Pole. In addition to that, what we also found is that there was organic material in the plume. And if you've got organic material, water vapor, which is coming from liquid water underneath the surface, and an internal heat source, then you've got 3 of the ingredients that you need for life to potentially form. The 4th thing that you need is for that system to be stable over a period of time. And that's the 4th ingredient that we're not sure of yet. This is another view of the plume, taken a few months later. And you can see these different colors of the different density of the plume. And so you can see, as you're getting further out, it becomes less and less dense. But it's a vast plume whose activity changes over time. And in fact, some of the cracks are opening and closing over time. So depending on where Enceladus is in its orbit around Saturn, sometimes some of the cracks open up and others close, and vice versa. So it's a very changeable system. This actually shows you some of the sources. So these little stars here show you, for this particular image, where material was leaking out. And so these are this is a temperature map lying over the cracks on the surface, and the yellow is the hottest temperature. And you can see really the sources are either on the edges of the hottest region or right on the hottest region. And so you've got this internal heat which is coming out. And that's a real surprise, because Enceladus is small, it's about 500 kilometers in diameter. You would have thought it had long since cooled down from when it first formed. And so there's some process taking place in the interior which is keeping it hot. The thought is that maybe back in its history, its orbit around Saturn was not quite as circular as it is now. And so if its orbit was elliptical, then on that region of the orbit where it was closer to Saturn, the gravitational forces of Saturn, tidal forces, would keep the interior molten. But it's work that people are still trying to understand. And I think this might be the last view, the last slide linked to Enceladus. This shows you data from one of the other instruments, which is called the iron neutral mass spectrometer. And so it almost tastes the region that it's flying through. And on a really close flyby, I think the closest flyby we had at Enceladus was 25 kilometers above the surface. They'll never do that again, because the magnetometer boom began to wobble because we were in such a dense atmosphere that they almost lost control of the spacecraft. So they're planning to lose control in 3 weeks' time, but they didn't want to do it before then. So this shows you the material that was found in the plume. There was methane, there was water vapor, simple organics and complex organics, and carbon monoxide and carbon dioxide as well. And something else they found in the later flyby was they found, God, I can't remember the name of it. It helps keep water liquid at at much lower temperatures. Sorry?
Glycerol?
And, well, it's essentially antifreeze, but it's got a much more technical name, of course, but I can't remember it. But they found that. They found this antifreeze thing in the plume. Of course, I'll remember at 3 o'clock this morning. Anyway, they found it. Whatever it is, and so they were quite excited to have found it, because that helps explain why we've got liquid water at these very low sort of temperatures. It was a real surprise that at minus 170 degrees Celsius we've got water in its liquid form. Okay, so that was Enceladus. I'm jumping around a bit here, but I wanted to talk very briefly now about the Jupiter mission before I move on to talking about the end of mission. And the Enceladus discovery, I think, helped to focus people's minds on some of the moons in the solar system. Moons that have liquid water under their surfaces, because Enceladus is not the only moon in the solar system that has got liquid water. 3 of Jupiter's moons do as well. Now, Jupiter's got 4 main moons called the Galilean moons. That's Io, Europa, Ganymede, and Callisto. Io's a very strange beast. It's got sulfur volcanoes on the surface, and so it's spewing out tons of sulfur. Europa has a liquid ocean quite close to the surface, we think. We think there's an ice crust, and then there's liquid water underneath the ice crust. Ganymede is a magnetometer person's dream place to go to, because it has its own internal planetary dynamo, the only moon in the solar system that does. And it too has got liquid water underneath the surface, but we think it's a bit deeper. We think the crust is maybe 100 kilometers in depth. And then this other moon, Callisto, also has liquid water. And so one of the things you can use my instrument to do is you can actually measure the currents that are flowing in the liquid water. And you can work out from those signatures not only how deep the ocean is, but what the conductivity of the ocean is, what the salt content of the ocean is. And that's one of the things we're going to focus on with the JUICE spacecraft mission, which is a European Space Agency mission. We're going to fly past Europa twice, and there's going to be this high inclination phase, so we're going to come up out of the equatorial plane, and we're going to make measurements on field lines that we've never been on before. We're going to fly past Callisto on 10 different occasions, and then for the end of the mission, for about 6 months, we're actually going to go into orbit around Ganymede. Because one of the ways for you to be able to understand the system is you need to spend time there. You need to work out if what you're seeing are temporal effects, so changing with time, or spatial effects are dependent on where you are in the orbit. I'm just trying to think let me just, before I go on to that. So this goes back to the needing lots of patience to be involved in planetary missions, because we first started talking about the Jupiter mission in 2012. We were selected by the European Space Agency to fly in 2015. We're building the instruments now. We will only be launched in 2022, and we will only get there in 2030. And so, in some ways, I almost see JUICE as a way of paying back, because I was really fortunate. I became involved in the Cassini mission as it was launched. And so all the people who worked on Cassini before that essentially gave a gift to the younger scientists in the community. And so I see JUICE essentially as a way of paying back for that. I'll probably sit there and gripe at all of my team members and tell them they're not doing things right, but I should be able to get a bit of fun towards the end of my career. Okay, so this is what we're going to focus on as far as the different moons are concerned. We're going to look at Ganymede. It's essentially the largest moon in the solar system. Titan is not quite as big, but Ganymede is the largest. It has this deep liquid water ocean, and it's also got this internal dynamo. And so we think by going there and understanding the internal structure better, it will allow us to understand many of the moons in our solar system, but also some of the exoplanets as well, because there's now a real focus on moons around exoplanets. As far as Callisto is concerned, we think its surface is probably the oldest surface in the solar system. So seeing how it is different to that of Ganymede, will allow us to get an understanding about how Callisto might have formed. And then Europa, we're only going to fly past Europa twice. The reason for that is Europa is quite close to Jupiter, and its radiation environment is extremely intense, and so instruments and spacecraft find it really difficult to survive there for any length of time. In fact, NASA, it was a long process, NASA and the European Space Agency, ESA, were going to do this together. We were going to have two different spacecraft. NASA would build one, and ESA would build the other. NASA then withdrew, saying they didn't have enough money, and so ESA decided to go it alone. 3 years later, NASA then said, oh no, we are going to do it. And so they're now building their own, but we're going to be launched at slightly different times, and we're still not quite sure if we'll be able to do it together. But if we can, that would be great, but we aren't dependent on it. Okay, so I want to talk about the end of mission now. The end of mission is due to take place on the 15th of September of this year, so 3 weeks tomorrow. And it's been planned so that we can safely burn the spacecraft up in the atmosphere of Saturn, because we don't want it to land on one of the moons. Because if in the future we find life on one of those moons, people might say the Cassini spacecraft took the bacteria there, so we don't want to do that. And the other reason we're doing what we're doing is that we don't understand the internal structure of Saturn. We don't understand its magnetic field and how it formed. We thought we would understand it after being there in orbit for 13 years, but we still don't. And so what we wanted to try and do was get inside of the rings. We think the rings are masking the effect of the signal from the interior. So if we can get inside of the rings, then hopefully we can better understand its internal structure. So the observations were designed, as I said earlier, with the magnetometer instrument and the gravity instrument in mind. And there were two different phases to it. One of them was called the ring grazing orbits, where this is, so here Saturn is, this is the orbit of Titan, at about 20 planetary radii away from Saturn. And Titan is being used as a gravity system, so we fly past Titan to give us a little kick to change the orbit. So we had 20 of these ring grazing orbits, where the closest approach was just beyond the edge of the visible ring. We then, and that started in November of last year and went on until April of this year. And then we got another kick from Titan, and we changed the orbit, so now we're actually going inside of the rings. And we're essentially just above the atmosphere. And the last couple of orbits that we've had have been actually going into the atmosphere. So we're slowly getting closer and closer. So we've got 22 of these blue orbits, which are called the grand finale orbit. And then the final orbit, which is this orange one, is when the atmosphere will essentially burn the spacecraft up. This is another view. It shows you how close we're going. So we're essentially about 2,000 kilometers above the cloud tops. And we had to be really careful. On the first few orbits, we flew with that high-gain antenna, that white umbrella-shaped thing. We flew with that moving in the direction of travel, so that it essentially protected the instruments and the spacecraft from any energetic dust particles that might be there. But this is the region that we've been flying in. We have an orbit every 6.5 days, so it's been really intense. Essentially, once a week, we're getting data back from these orbits. And one of the things we want to try and understand is how the magnetic field of Saturn is generated. So these blue field lines here is what we measure when we fly close to Saturn. And what you do is you use what these signatures are telling you to get an understanding about what's going on inside. We think what happens in the interior is there are lots of things taking place, but there's an overturning convective motion. Heat has been given off. You've got rotation of the interior as well, and those processes combine to form these field lines that you can see here. But as I mentioned at the start, one of the real surprises is that planetary dynamo theory says if that's the rotation axis of the planet and that's the dipole axis, that's the magnetic axis, you need there to be a tilt. If you don't have a tilt, the magnetic field can't be generated. At Saturn, we can't measure the tilt, and we just don't understand that. We don't know how that can be. And so you could almost describe the magnetic field measurements and the gravity measurements as well, almost as a way of seeing inside what's going on. You can't get there because the spacecraft's going to burn up before you get to the interior, but you can use the measurements you get outside to get an understanding. What we think is happening is we know that Saturn is made up mainly of hydrogen. And so what we think is we've got the atmosphere outside, of course. We've got molecular hydrogen, and then we've got a layer of metallic hydrogen. And it would need to be metallic because the way the magnetic field is generated is currents flow. And so what you need to do is you need to strip electrons off the hydrogen atoms and make them metallic, and that would allow the current to flow. So we're hoping with our data we're going to be able to work out what size the core is right at the center, what it might be made of, and then also what the size of the dynamo region is. This is the region where the magnetic field is generated, and why you can have a magnetic field generated if you don't have a tilt. And that's the really big question, and we just don't know the answer. I'm not going to talk about that. So this is a view. If you were riding just behind the spacecraft, this would be the view of what we've seen for the last 19 orbits, so the last 19 weeks essentially. We've now got 3 more to go, but we're essentially skimming just above the atmosphere. And I'm going to end by playing you a movie, she says. Here we go.